EEE 145, Chapter 6, Protection Fundamentals 2, Day 2. All right, today we're going to talk about distance protection, which is another form of protection typically used for transmission lines. And so here, let's go ahead and figure out, well, what does a 21 distance relay do? This relay uses impedance-based calculations to decide if we should trip or not. Now, how do we figure out the impedance of a fault when it happens? Well, fault impedance ZF can easily be calculated by looking at your voltage on your power system and divided by the fault current that's happening. We could easily find this because voltage can come from a VT on the substation and fault current can come from the CT at the substation, both connected to the 21 relay. So here, if we have a fault and then the 21 is continuously monitoring the system, it's going to notice that we'll have a low impedance. A low Z impedance is going to correlate to a higher current. Okay, so if we drastically see the impedance lower because a fault just happened, the current will shoot up and the relay can sense that this will be a fault current. And then if it's a fault current, then we could decide to act and trip the line off. So we could save the power system. Okay, now let's talk about how do we figure out this impedance calculations and how can we sense where the fault is on the power system? Well, here, let's analyze that we have a fault at the remote end of the bus of the line. So bus B, the other side of the power line, we have a three-phase bolted fault. Now, so from our point of view, so we're at the 21 relay right here, looking into the line, I can calculate my fault current, my fault impedance to be 10 ohms, right? Because remember, when the fault happens, that returns to the source, and then the only thing stopping the fault from going infinite impedance is the system. And the only thing that's stopping the fault from going to an infinite current level is the line impedance here. So if I can calculate in the relay that my impedance is at 10 ohms, I can then know that this is a fault 100%. So it's a fault 100% down the line. And we call this a remote end fault. Okay. Now, let's go ahead and ask ourselves, what will happen if we have a midline fault? So if we have a fault roughly in the middle of the transmission line, the 21 relay is going to sense the current and do its calculation, and it's roughly going to sense that the current is about 5 ohms, right? And then this is going to help us see what's happening, and it really would dictate that, oh, well, at 5 ohms, that's 50% down the line. Okay, so the fault is 50% down the line. And this is really good for us because then we know roughly where to go. Remember, transmission line could be 100 miles long, so knowing about halfway through is much easier for the line crew to go out there and pinpoint where the damage is versus traveling 100 miles looking at the transmission line poles over and over trying to figure out what's wrong. Okay. In addition, the relay can sense that, oh, the fault is on our transmission line, so we should trip the circuit breaker. Okay. Now, lastly, what happens if we have a fault close in? Right. So if we have a fault right outside our substation, what do you think is going to happen here? Well, the fault impedance calculated by the relay is going to be very small, like 0.5 ohms. And then the relay can then say, hey, we have a fault only 5% out into the line. So it's the fault is 5% of the line. It's almost at the substation. And so again, it's good. The nice thing about this relay is it can tell is a fault within my transmission line or not. So for example, we have a fault really far down the transmission line, the impedance is going to be higher than 10, So then we could sense that maybe this is not our line, it's somebody else's line, somebody else's problem. So maybe we should hold off before we act. Okay, remember, I'm mainly responsible for my transmission line, right? Not the ones five lines over or like in the neighboring utility. Okay. So just the fact that this relay can detect where the location of fault is a huge advantage versus other relays like overcurrent relay. Overcurrent relay does not have any fault detection. Oh, sorry, it doesn't have any way to figure out where the fault is on the power system. It either knows there's a fault or not. It's a binary number. Distance protection here can give you a more precise location, and it give us more options to play with. Okay. So with that, we talk about more options because we can sense where the impedance is on the transmission line or in the power systems. We could set up multiple zones of protection to where one relay at substation A can serve multiple purposes. So at this substation A relay, distance relay is 21, looking into the line, well, we can say we have 3 zones. Zone 1 is up to 80% of the line. So if we have a fault at 80% or less, we should trip with no time delay. So trip with no time delay. Okay. So what this means is if I have a fault and my relay calculates a fault impedance and dictates, hey, this fault is 70% of the line that's within my zone 1, I should trip immediately. Okay. Now we could have a zone 2 to cover our neighbor substation B and maybe a little bit of the transmission line adjacent to us. And so this zone 2 will activate if we have a fault up to 100% of the line plus 20%, so that's a plus, of the adjacent line. So our neighboring line. Okay. Now, we want to give substation B time for their relay to operate first. So we're going to put a 20 cycle delay on our zone 2. So if we have a fault at substation B, we'll give 20 cycles for substation B to solve the problem. If it can't solve the problem in 20 cycles, something's wrong in the substation B. So we're going to step in as a backup protection to help. So remember, zone 2 is kind of a backup system. We could even go a further level and have another backup zone, zone 3, and that could cover up to 100% of the line plus 100% of the adjacent line as well. So this is not only covering our line fully, we're covering the next line fully and substation B and substation C. So this is like the backup of the backup. So this is backup squared. Okay. Now, again, we need to let the main primary protection operate first, even let the backup protection operate. And if both of those fail, then we'll come in and save the day. So we'll give everybody a 50 cycle delay for their systems to operate first. But again, if their systems don't operate, we're going to come in as a last line of defense to save the day at 50 cycles. Okay, so those are your 3 zones of protections you'll typically see in any distance relay you use. Now, again, these percentages aren't hard numbers. Some utilities can say, well, my zone 1, I want it to be 85% or 90% or 70%. It's really up to you as a protection engineer what you feel comfortable with. Okay, same thing for zone 2 and zone 3. These numbers I showed you are just good rounded typical numbers most people use. But if you have a reason to use something past these numbers, You can modify it a bit. I think you'll be okay. Okay. So with that being said, let's go ahead and kind of do a quick analysis and see how these zones operate together. So again, we have our 21 relay. We're looking into line AB, and we have a fault 50% down the line. So we have a fault midpoint between substation A and substation B. So the question is what will each zone do? Well, for zone 1, easily it's inside the zone. 50% is less than 80%. So inside our zone, we should trip instantly. Okay. Now let's go to zone 2. Is it inside zone 2? Technically, yes, it is inside zone 2. We should wait 20 cycles, but zone 1 tripped instantly. Because zone 1 tripped instantly and stopped the fault from happening, zone 2 never had a chance to operate. Because remember, we have to wait 20 cycles. Okay. What about zone 3? So technically it's inside zone 3 as well, but same thing with zone 2. But zone 1 tripped instantly, so we could never wait that 50 cycle timer to have a zone 3 trip. Okay. So at the end of the day, it's really zone 1 was the zone that saved the day, because it's close in. We should trip it. It's our responsibility, trip as fast as possible. Okay. Now we could go to a zone 2 fault. So here, let's have a fault at substation B right here. Let's do our analysis again with a 100% line fault 100% out of our line. So zone 1, my relay will calculate, oh, what's my impedance of the fault? It's going to be roughly 100% because it's at the other substation. So our ZF is going to be 100%. Okay, for zone 1. Because 100% is more than 80, this is outside our zone. Outside zone 1. Because it's outside zone 1, we're going to ignore it altogether. So no tripping, no action at all. Ignored. Okay. Now let's look at zone 2. This one, it's inside our zone because remember, zone 2 is 100% of the first line and 20% of the next line. This is easily 100% of our line, so it's inside zone 2. So because it's inside zone, we're going to start counting down 20 cycles. Now, is anything going to trip before 20 cycles? Well, zone 1 would have, but we ignored it. So we're going to wait 20 cycles, then trip. Now, this is assuming that substation B protection didn't operate, right? In real life, substation B should operate first, but in case it doesn't, this will be a 20 cycle, then trip as a backup protection, okay? Now, what about zone 3? Is it inside zone 3? Technically, yes. Right? Zone 3 covers 100% of the first line, 100% of the second line, but it won't do anything because zone 2 tripped at 20 cycles. So remember, zone 3 started counting, but it has to count 50 cycles. So it counted all the way to 20 cycles, and then zone 2 took over. Okay, so zone 3 still had 30 cycles left, and it dropped out. So in this particular case, it's zone 2 that would that this relay would activate if called upon. Now, let's go look at zone 3. This will be a fault 50% on line BC. So it'll be about right here. So you could probably see a pattern evolving where you can guess which zone this fault operates in and what each zone does. Versus zone 1, it's clearly outside the zone, so it's no trip. Zone 2, again, outside the zone. no trip. Now, zone 3, it would be in zone because 150% is less than 100 plus 100, right? So it will be inside zone 3. Now, remember though, we're gonna have to wait 50 cycles to trip. But we will trip if nothing happens within 50 cycles. So this is how you could take one relay and really stretch its reach out far, far, far past your own substation and your own transmission line. That's why people like distance protection, because one relay can cover a very large amount of ground and multiple devices and serve as a primary, a backup, and then a backup of a backup. Okay. Now, so we established all the zones. We talked about the 21 relay checking impedances, but I want to be more exact on how does a relay the numbers actually calculate. Because remember, the relay itself does not take primary line current and primary line face-to-face voltages. We have CTs and VTs to bring it down to a secondary level. So let's kind of remember ourselves. The secondary current going into the relay, I secondary, which is right here, by the way, this is I secondary, is always going to be I on the primary line divided by the CT ratio. Same thing for voltage. You're going to have your voltage right here, V secondary. Okay. What is that voltage? V secondary is always V primary divided by the VTR, voltage transformer ratio. So whenever we calculate the impedance in the relay, technically, it's actually a secondary impedance that the relay is seeing, not the actual 10 ohm line impedance. Now we can calculate the secondary impedance. The relay automatically does the math for us. It knows it needs to do Ohm's law on secondary voltage and secondary current. Doing a little arithmetic, putting these first two equations in, you can find out it's actually the CTR over VTR is a ratio change from the primary impedance. Okay. So if I have my Z primary at 10 ohms here, in this particular case, this is 10 ohms from our image. We're going to have to multiply by the CTR over VTR ratio to get the secondary impedance. This is what the relay sees. Okay. So you might, when we do our calculations and our settings, we will have to take this into account and kind of play around with the CTs and PTs to get the actual impedance to put in the setting of the relay. Okay. So kind of showing you some numbers to see, how the math works out. Let's say we want to cover 80% of the line. So right here, I want to cover 80% of the power line in a zone 1. So right now, I know from this relay, I'm going to look down to about right here and call this 80%. Okay. So what will be the steps I will look to put a setting into the relay? Well, first thing is we need to know what the total line impedance is. So 100% of the power line is a full impedance, which is 10 ohms. And I'm going to say primary because this is the impedance on the actual power system. Now, when I want to calculate 8%, I know my zone 1, which is 80% of the line, is going to be 80% of 10 ohms, which is 8 ohms primary. Okay. Now, the big trick is the setting calculation inside a relay is going to take secondary current or secondary impedance. So we're going to calculate Z1 as a secondary impedance. So we're going to take our primary impedance and multiply by the CTR divided by the VTR ratio. Now I know I want to do it for 80%, so my Z primary is 8 ohms. My CT ratio is 600 to 5, which is a 120 on top. My VTR on the bottom is 69 to 115, and that should be 600. You can check the math if you want. And when we calculate all this, our Z1 to put inside the relay is actually 1.6 ohms. And again, this is in secondary impedances. And this is the relay setting that you will put into the relay itself. Okay. So all this time we've been talking about zones and primary, 8 percentages. Just remember, when you actually do the relay calculations, you're going to convert it to the secondary impedances through the CTR VTR ratio. Okay. So with that being said, let's talk about trying to figure out some impedances, right? So, or some zone settings. So here we have a transmission line. We have between line AB, which is 10 ohms. We got line BC, which is 20 ohms. You got your CTR, your VTR. I want you to calculate the zone settings for this distance relay. I want you to calculate zone 1, which is 80% of the line. So give me a impedance and secondary impedances, what we just did. Give me a time delay to put into the relay. Do it again for zone 2. Give me a secondary impedance, which is 100% of first line plus 20% of next line. Give me a time delay for this zone 2. Let's do zone 3. 100% of first line, 100% of second line. Don't forget, you got to put in secondary impedances. And give me a zone 3 delay. This is pretty much every protection engineer's job. I want you guys to take a stab at it. Take about 15-20 minutes to do this. We'll come back, we'll check your work and see how you're doing, okay? So talk to you in a little bit. All right, welcome back. We're going to go ahead and check the distance protection settings calculations you did previously during the break. So let's go ahead and start for zone 1. So remember, zone 1 settings are always in secondary impedances. So our Z1 is always 8% of the actual line we're looking at, which is 10 ohms. So it's 8 ohms primary. We convert it to secondary. Our CTR is 600 to 5, which is 120 on top. You divide it by 69 kV to 115 volts VT ratio, and that's a 600 flat. So 120 over 600 multiplied into 8 ohms gives us 1.6 ohm secondary. So the 1.6 ohms is what you would put into the relay as a zone 1 setting. You put it at a 0 cycle delay because zone 1 should be tripped instantaneously. Here we have zone 2. Zone 2 is going to be 100% of the first line plus 20% of the second line. A common mistake a lot of engineers do, they just do 120% of the first line. That's actually incorrect, because if you look at the second line is longer and has a difference in impedance than the first one. So zone 2 is 100% multiply into 10 ohms, which is the primary line we're on, plus 20% of 20 ohms, which is the adjacent line. So you add those all together, you get 14 ohms primary. And going through our CTR over PTR ratio, we get 2.8 ohms secondary. Again, this is zone 2, should have a 20 cycle delay. Going ahead and doing zone 3, kind of very similar, except we do 100% of first line, 100% of second line. So Z3 is 10 ohms plus 20 ohms, a total of 30 ohms. Go through our CTR over VTR, we get 6 ohms secondary. And remember, this is a 50 cycle time delay. So one thing you should notice is as a zone, we go down to zones from 1, 2, and 3. Your impedances typically get larger because you're covering a longer distance with the this zone. Additionally, your delay should get higher and higher because the zone 3 level should always have the largest delay. Zone 2 should have the middle delay, and zone 1 should have no delay. So as you go down the zones, it's increasing time delay. There's a little pattern to look at. Okay, so here we're going to talk about what it takes to actually cover the line. We call it a full protection of the power line. So far, we talked about relay looking down one side of the line, but remember, which way does a fault current flow? If there's a fault in the middle, fault current will flow from both sides in the transmission line. So you have IF1 coming on one side, IF2 coming from the other side, right? So because in transmission lines, we could have multiple sources everywhere, you have to completely disconnect the power lines on both sides to fully isolate it. So which way does a fault current flow? From both directions. So in that case, how can we fully disconnect the power line to extinguish a fault? Both sides of the line must be disconnected. So we must disconnect both sides of the line. So that means we need a 21 relay at both ends, looking into the line. So at the edge of each line is a substation. You'll have one relay looking in and another one looking in from the other side. So this relay will look inwards that way. And then, so relay B looks inwards from the right-hand side. Relay A looks inwards from the left-hand side. That way they're both looking in and both covering the line. Okay, let's kind of see how this will work in having a fault. Now, I'm going to show you what the worst case fault would be. And that would typically be a fault close into a substation. So they say we have a fault right outside one substation. The reason why this will be kind of bad, or the worst case, is because this fault is not covered by zone 1 on one of the relays. So let's go ahead and analyze. So looking at relay A here, how fast would relay A act? So remember, relay A is looking into the line this way, okay? So it'll actually act pretty quick because a fault is right outside the substation. So this relay would see a very low impedance. So relay A might see half an ohm, 1 ohm, very, very small. So it'll have a zone 1 fault and it'll instantly trip. Now, if we look at relay, and this is relay A. Okay. Now, let's go ahead and look at relay B. So relay B is looking into, well, let's draw it like the other one. Relay B is looking into the line from the opposite side, right? But for relay B point of view, the fault is actually very far out. It's about 95 to 98% of the line. So relay B will see a zone 2 fault because it's greater than the 80% of a zone 1. So how fast will distance relay B act? This will be a zone 2, and this is a 20 cycle trip. This is relay B. So you got to ask yourself, putting everything together, what was the total clearing time? Now, if you notice, relay A acted instantly, and it cut off the left side of the line, but the right side of the line is still active, even though we tripped the other side. So technically, we won't totally clear the fault until 20 cycles later. So that's a total clearing time. So that's why I say it's worst case time delays. You guys see on both sides of the line, which one, what are the timing for each one, and the worst case of the two is your total clearing time. Now, a little side note, people ask, well, why do we do 80% of zone 1 and not 100%? The reasoning why is if we do 100%, we might accidentally go into substation, the neighboring substation. And CTs and PTs are not 100% accurate. So if we put 100%, we might accidentally zone 1 trip for the other substation, which is bad because we're instantly tripping. We're not giving any other relay a chance to operate, right? So just as a safety margin, let's dial back to 80% to just give the other substation a little bit of time to operate. So that's why we do 80% of zone 1, not 100%. Now, obviously, the downside is right here, where that last 20% of the line will take 20 cycles of cover instead of fully instantaneous, which, again, protection engineering is always you get one benefit, you give up something else. So it's always a compromise, right? And we're okay with this type of compromise here. I'd rather have a 20 cycle delay on these small worst case scenarios than accidentally tripping the wrong thing when I'm out of my zone and causing a misoperation. Okay. Now, let's go ahead and look at the larger scale where we have multiple lines, multiple relays. We're just layering everything together. Okay. So here, if you look, how many layers of protection will each transmission line have? So let's kind of just draw a dotted line right here. If I have a fault right here, how many layers do I have? Well, I have, looking into this way, I got one layer here as my primary, which is at this substation. And then got a second one as a backup, which is all the way back here at this substation. So looking on one side, I have 2 layers of protection. We could do the same analogy coming from the other way, looking from the right-hand side. Well, right here, I have my first layer of protection, which is from the substation near me. That's a zone 1. And I also have a second layer of protection, which is a substation 1 away over here. So you can see no matter where you are on the transmission line, you will always have at least one layer of protection, which is the 2 substations next to you connected to the line. You will always have at least 2 layers from the adjacent substation looking into you. Okay. So let's kind of sum this up. How many layers of protection would each transmission line have? Every section has at least 2 layers. Okay, which is a primary and a backup. So where's the primary protection located? We just say it, we'll put in typing, writing, the relay watching, well, let's write. The relay located at the substation connecting the lines. Okay. So you have a transmission line, both substations connected to transmission lines. That's where the relays are located. And this could either be a zone 1 or a zone 2, depending if it's that last 20% corners of the line being faulted. Excuse me. So at this particular point, where's all the backup protection located? The relay is located at the next substation. Right? One line, we'll say the next substation past the primary relay. So remember, the primary relays are the substation next to us, the substation past that. So may relocate it at the next substation, or maybe we'll say the relay located at the I'm gonna say substation past our substation. Okay. So I just kind of may word it a little bit. Relay located at the substation past our substation we're looking at. Okay. So in this case, this would be backups for our line. This will be a backup relays. That's where they're located. Primary is located right here. Primary is located right here. Okay. So that's, as you have more transmission lines, you're just going to layer this all over the place. So eventually your entire district is blanketed with in zones all over the place, and you have no gaps. That's the ideal solution. Okay. So putting everything together, distance protection is a tried and true old school protection. We've been using it for over 100 years, right? So it's a staple of any type of line protection you'll see. One relay can cover multiple lines. So one relay at substation can carry our line and then the line over. That way we have multiple layers of protection. So zones protection can reach multiple lines. We can create primary and backup protections for each line that we have. These distance protection can have fast response if there's zone 1 primary protection. Directional, so the relays are directional, so there's less chance of misoperation. So if you notice, the relays only look into the line, they don't look behind them, right? Does not require any form of communication, unlike a differential relay where you need to communicate to a second relay, or you need more than one CT input. This relay only needs the VTs and CTs at its location. It could work independently of any form of communication or anything else that happens in the power system. That's why people like it. It's a very self-sufficient, self-contained protection scheme. So I want to say thank you for hanging out and checking all the different type of protection schemes. So we're going to go ahead and call it here, and we'll come back next week and start talking about more details on specific equipment and how to combine all the types of protections we've learned, all the CTs, VTs, all the breakers, everything put together, and we're going to talk about a full package protection plan for each individual type of equipment you'll see out in the power system. So thank you for showing up, and we'll catch you guys later.